Welcome everyone. In this video we are going to discuss single slit diffraction. Single slit diffraction. This was in fact a video idea from one of my viewers. They wanted me to make a video about single slit diffraction, and here I am making a video about it. I wish I had done this earlier, but I was kind of a bit busy, so sorry about that. I could only get the time to do it now. That's why I'm doing it now, okay? I hope it is still useful for the person who requested it, and otherwise anyone can watch it, of course. Anyway, so what is single slit diffraction? Well, as you can guess from the name, there's going to be a single slit, like so. And then, let me draw it a bit better. Sorry about that. Yes. And then there's going to be a screen where we record the result of this diffraction. And let's make the gap a bit wider. Okay, maybe like that. Cool. Now, what happens is we're sending light through the slit and there is a diffraction pattern. This is very interesting because, think about it. If there are two slits, okay, fine. If there are two slits, the light can interfere with each other, so then there can be diffraction, right? The light that comes out of one slit interferes with the light that comes out of the other slit, and they diffract. That's cool. But how can there be diffraction if there is only one slit? The answer is there is still interference. So this is due to interference. But what is interfering with what? The answer is light is interfering with itself. Hold on a second, can it do that? And the answer is yes, it can do that. For that, let's first draw the wave though, and then we will discuss how it can happen. So we have the light waves. They are coming from a source far away. Let's say it doesn't really matter. They're coming parallel though. Let's think of it in parallel. Okay, they are coming parallel. Well, not parallel actually. They are coming perpendicular to the surface, to the slit, okay? So we have these waves, and what I'm going to use is a principle called Huygens principle. Huygens principle. This principle tells us that we can interpret every point on the wavefront, and this is a wavefront, they are called wavefronts. We can interpret every point on the wavefront as a new source for another wave. So Huygens principle says this point on the wavefront, it is actually a source for wave, and it's going to be producing a wave itself, like so. And this point, it is also a source. It is going to produce another wave. And in fact, these waves are called wavelets. So basically Huygens principle says, well, every point on the wavefront is a source for wavelets. Wavelet is a source of wavelets, let's say. Okay? And the thing is, you don't need to accept this. You're like, hold on a second, how can this work? Well, the thing is, all of these wavelets, all of this infinitely many wavelets, they all interfere all the time, and their interference results in the new wavefront. So all of these guys, and I didn't draw them, I just drew two, but there is here, infinitely many. And infinitely many of these interfere to produce the new wavefront. Okay? So the thing is, the wave was already interfering with itself all the time. But once we place a slit, it is only then that we can notice it. Because what happens when the wavefront reaches the slit? let's say we draw another wavefront here, okay? And they should be evenly spread out, but I'm trying my best, okay? So we have this new wavefront, and normally there is a source of wavelet here and another one here. Now this guy is fine, it is doing its job as usual, but this guy, it can't do its job because now there is the wall, it can't pass through, and as a result, since before all of them were evening out and giving the same wave that we started with, giving the same wavefront, since we are losing some on the sides here and here, we end up seeing a diffraction. And what is that diffraction? Okay, so I tried to explain why there could be a diffraction in a single slit, and there in fact is a diffraction. This is very important for this experiment, let's say, because, I mean, when you think about it is kind of confusing. There is a single slit and there is a diffraction. How can that happen? It happens due to Huygens principle. Light is always interfering with itself when we adapt Huygens principle point of view. When we adapt that point of view, it is always interfering with itself, but only when we have a slit, we can observe that there is in fact an interference, okay? So that's what's happening. And what is the result though of this interference? Once the light passes through the single slit, and this is experimentally observed, as far as I know. I never did this myself, but I mean, we read about this all the time. But I would love to do this myself one day, hopefully. And the result is there is a very prominent peak at the middle, and this is exactly in the middle, okay? This is symmetrical, and you would expect it to be symmetrical, right? Why shouldn't it be symmetrical? I also said that the light was coming perpendicular to the walls, to the slit, so we would expect it to be symmetrical, and it is symmetrical. And then there is going to be little peaks. Let me draw it a bit better. Sorry about my poor drawing skills. There are going to be like peaks like so. Okay? And I mean, these peaks are also interesting. Why are they there? Well, we are going to kind of discuss it, how that happens. But they are very small compared to the prominent peak at the middle. So what we want to do first of all is let me draw the platform a bit to the left so that there are 0 spots, because we are going to calculate them, okay? Alright, like so. Cool. Now, there is one of the things that we can do is, we can ask the question, where is this minimum, right? Like here, and I drew it very bad. Excuse me, I'm sorry about that. Like, for example, here, there is a 0, and there is a 0 here as well. When does that 0 happen? When is it that all the lights deconstructively interfere? All of them cancel out. So what is this point? That's a question that you could ask. You could also ask, what is this point? You could ask, what is this point? Okay? And of course, you can also ask, what are these points? Okay, where are those? And let's first start with this one. So the way we will answer where it is, we're going to answer the where question using an angle. We're going to give the angle that it is at. And that angle is relative to the middle of the slit. And we're in fact going to define this angle as theta, okay? That's theta, we want to find theta. Now, we are going to use a very cool method to do this. And I'm going to erase this wavefront so that we have space to work with. Okay? So now, yes. What is the method that I'm going to use? Well, the light wave was passing through the slit, right? So the wavefront is here. Some of it couldn't pass because of the walls, but the rest is going to pass through the slit. And since we are using Huygens principle, we can select as many points as we want on the wavefront. Let's say that I select 2 points. I mean 4 points. Well, yeah, 4 points. We could do 2, but I mean, actually, no, 2 wouldn't be enough. We need more than 2 for the argument that I'm going to make. So 1 is going to be here, and let's use a different color. 1 is going to be here, and I want them to be evenly spaced out, so all of them are quarter of the way away from each other, quarter of the length of the slit, which oftentimes is called W, so width of the slit actually. W is the width of the slit, and the distance between each point that I select is W over 4. So, like this, okay? This is exactly the middle, so even though it doesn't look like that, this is W over 2 and this part is W over 2. Cool? Now, the argument is this. I am saying that this, and well, I drew it so bad. I'm sorry about that. Well, hold on. I need to do it a bit like this. Okay. Cool, like this. So the argument is, if this light, it's going directly to that point, and this light beam, if they are destructively interfering, I claim that all of the other guys will also destructively interfere. And how do I make that claim? So first of all, I need to show that these two interfere destructively. And for that, well, I'm going to focus on the path difference between the two. So if I draw a perpendicular like that, perpendicular line, dashed line, this distance is delta x. And so I will write for destructive interference, well, delta x should be what? It should be half a wavelength, lambda over 2. Or it should be 3 times half a wavelength, or 5 times half a wavelength. And you might be saying, how do you come up with this idea? Where do you know that it should be delta over 2? Well, not delta, excuse me, lambda over 2. Well, if you have a wave like this, for it to have destructive interference, the other wave should be shifted a half wavelength. And if you shifted a half wavelength, it's going to be like this. Right? These will align if I were to draw them neatly. And so if they are half a wavelength apart, or 3 times half a wavelength, 5 times half a wavelength apart, the waves interfere destructively. That's what we're using here. So using that idea then, and using also a bit of trigonometry, we can see this is going to be 90 minus theta, then this angle is also theta. So what is, I don't know, like sine of theta? Sine of theta is going to be opposite over the hypotenuse. So opposite is delta x, which is lambda over 2. And what is the hypotenuse? It is this part, which is w over 2. W over 2. 1 over 2 simplified, they are simplified. So we see that lambda is equal to W sine of theta. And in this case, we are going to get destructive interference. And so if we are also looking for theta then, well, what is theta? The first minimum point, it is arc sine of lambda over W, okay? And hold on though, I skipped a part. I said if these two interfere destructively, if this and this interfere destructively, all the others would also interfere destructively. How do I know that? Well, because I can pair up all the points. I could use this point and this point. I could draw the lines from those points to the point of interest, to the minimum point. And the same thing would happen. The same argumentation would be made and we would reach the same result. Okay, so the key here, we can pair up the pair up the sources of wavelets. And since the calculation is the same for all of the pairs, and one of the calculations show that there is destructive interference, this means that all of them interfere destructively, okay? And, I mean, we just drew 4 of them. We could also, there are also this point and this point. The thing is that the pairs are separated by W/2. And they interfere destructively, okay? Now, this gives you the location of the first minimum. For the second minimum, what you would need to do is, well, the thing is, you don't need to pair these up. You need to pair these up, but you don't need to divide them so that there is a difference of not omega, and there is a difference of W/2. You can also make it so that there is a difference of W/4. And in that case, and if you do that, I encourage you to do that, you would see that the second minimum, which we can call theta 2 then, so this is theta 1. For the second minimum, it would be such that 2 lambda equals W sine of theta 2, so you can figure out what theta 2 is. And in general, for destructive interference, W sine of theta should equal an integer times lambda. And this integer can be 1, can be 2, can be 3. And you can also already see how it can be 3, right? I mean, we don't need to have it lambda/2. It also interferes destructively. It is 3 if it is 5 in front. So we see the odd ones, odd integers make perfect sense. For the even ones, you need to do it yourself and see that we don't need to divide it like W/2. The distance between the pairs doesn't need to be W/2. It can be also W/4. And in that case, well, let me even do it quickly. So it is sine of theta 2 this time. It is, let's say, lambda/2 still, but it isn't it is W/4 this time. Okay, so this simplifies. There's a 2 which you can put here. You see that lambda is 2W. Hold on, did I make it wrong? Yes, I did do it wrong. Sorry about that. So it was, man, I'm making a lot of mistakes in this video. Sorry about that. So it's going to be sine theta 2 equaling 2 goes up front like that. Okay. Yes. And as you can see, 2 lambda equals W sine of theta 2 is also a destructive point. So it makes sense for all the integers, odd ones and even ones. But it can't be 0 though, right? And shouldn't be 0, because if it is 0, well, then we're just interested in at this point, and that is going to be a constructive interference point, as we can see from the experimental results. So n is 1, 2, 3, 4, 5. Any integer, any positive integer basically. It can't be 0. 0 is not a positive integer. Okay? And now for the constructive interference part, it seems as if you can make the same kind of argumentation. I mean, if we were to say, okay, let's find where the constructive interference happens. Let's do that with green. So we would use these 2 points maybe, right? And then we would say, okay, sine of, so we are interested in delta x. The path difference should be lambda this time, so that they interfere constructively. And we can say that sine of theta is equal to, we are looking at this triangle this time. Well, it should be equal to delta x, which is lambda divided by W/2. So lambda should be, so 2 lambda should be W sine of theta. But wait a minute. We just said that 2 would give destructive interference. How come that this is giving constructive interference? The thing is, the first calculation was right, but this is wrong. It is wrong because in the case of destructive interference, since every pair is cancelling out with each other, at the end, all of them add up to 0, right? Logically. But here, even if every pair interferes constructively, they don't interfere constructively together. What does that mean? Let me show you. So the first pair, maybe it's like this. Okay, you have it. And we are doing the phases. So the first two pairs, they are here. They are lambda apart from each other. They are in the same phase, and they are going to constructively interfere. Cool. Now, we would do the same calculation for the second pair. So yes, they would also constructively interfere with each other. Maybe this is the second pair. They are lambda away and they constructively interfere. And for the third pair, maybe they are here. They also constructively interfere. And for the fourth pair, which is, I know we can do it with pink, they would also constructively interfere, okay? This interferes constructively with that, and I don't know let's switch back to blue. This guy interferes constructively with that, but they don't interfere constructively together. That is, I don't know, these two guys, this pair is not constructively interfering with this pair. They are not in phase. Okay, do you see the nuance of the argument here? For the destructive interference, since they all cancelled out, the phase of them didn't really matter. They all cancelled out anyways. But here, since they are adding up, at the end their phases are not the same, so they don't constructively interfere altogether, even though individual pairs are constructively interfering. I hope this is clear because it might be a tricky idea. And in fact, this is why these peaks are relatively small compared to the middle one. Okay? I mean, these pairs, when we combine all of them, they mostly destructively interfere, and there is just a tiny bit left that we see on the screen. And in fact, from what I've been told, I'm not going to act as if I did the calculations. From what I've been told, from what I've seen from the material that I studied, figuring out where the constructive interference happens is a lot trickier than the destructive interference. Okay, this is an exact result for the destructive one, but for an exact result for the constructive one, you would, as I said, from what I've been told, you would need to know much more physics to figure out where the constructive interference would happen. So if anyone from the viewers knows how that is done, please share your knowledge with us in the comment section. But as a thumbs up rule, as a rule of thumb, well, if you want to figure out where the peak is approximately, you can just figure out the points for the destructive interference, so this point and this point, and you can figure those out exactly using this formula. This is exact, and from that exact calculation, you just take the average of those. You just half the value, and the constructive interference will happen in between those two destructive interference points. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.